Hi, everybody. Welcome to 3.5, which is sort of a mirror to 3.4 in that it's the same kind of conversation. We're talking about algorithms, but here we're going to talk about multiplication and division. We're also going to talk about exponents early in this section just because that sort of fits in with the idea of multiplication. So multiplication algorithms and division algorithms are sort of the most complicated elementary school math, right? They are the things where kids spend the most energy and where teachers spend a lot of energy learning to develop fluency. So that's the ability to do things quickly and correctly. With standard algorithms, with a variety of algorithms, you are going to see things in this section that you may have used before, that you may not have thought of. And that might make things a little bit easier. We'll see. But before we go there, there is some review of exponents in here because we use them in bits and pieces as we go. So remember that a to the n is defined as a is the base, n is the exponent, right? And, oh, sorry, I don't have the, whoa, pen set right. Come on, I want to use my marker. There we go. There we go. So a and n are whole numbers. A to the n is that many a's, and a to the first is always that thing. Anything, remember, to the 0 power is always 1. There are some rules here. So if I have a to the m power and a to the n power, I can add those exponents together. When you get stuck with rules like this and you don't remember how they work, what you should do is go back to numbers. And I always think like I have 2 squared times 2 to the third. Well, that means I have 2 2's multiplied together and 3 2's multiplied together. Well, now I have 5 2's multiplied together, right? So 2 plus 3 is 5. Okay. The second rule is power to a power. So when I have an exponent raised to another exponent, those get multiplied. So again, think of this like numbers, right? So if I have 2 squared, that's a 2, raised to the third power, what I'm really doing is 2 squared 3 times. 2 squared, 2 squared. So that's 2 2's times 2 2's times 2 2's. That gets me 2 to the 6th. Then 2 times 3 was 6, right? When I have 2 bases to the same exponent, I can multiply the bases. I can go in either direction here. So I can have a number to an exponent and I can actually take it apart for its factors. So let's say I have 10 to the power of 5. What this says is that I could actually rewrite this as 2 times 5 to the power of 5 and 2 to the 5th times 5 to the 5th and have those be equivalent things. They mean the same thing and they're the same quantity, okay? Or I could start with 2 to the 5th times 5 to the 5th and write it as 10 to the 5th. As long as the exponent is the same, this is okay. But if I had 2 to the 3rd times 5 to the 4th, that doesn't work. I can't do this process. If I divide exponents, I really subtract them. So where you see this more is in fractional form, right? So if I have 2 to the 3rd up here and 2 to the 1st on the bottom of the fraction, what I'm really doing is canceling, right? There's 3 2's up here, 1 2 on the bottom, cross them out. I'm left with 2 2's on top. But what I really did from an exponent perspective is 2 to the 3rd minus 1, 2 squared, okay? You can always sort of get yourself back into these by using just 2's. If a and m and n are natural numbers with m greater than n, oh, where does this one go? Sorry, my brain, I'm trying to figure out what we're trying to accomplish here. Oh, we're just what we just did. So this is the same as basically what we come to is that if we solve this like an equation, we can prove that this is true. We don't need to go through and prove this. I'm not sure it's going to help your cause right this second. I forget that slide is in there. Sorry. All right, and then the last thing is a to the 0, a to the 0, anything to the 0 power, anything is 1, okay? Every time, that's how it works. So that's some exponents. What we can do is use these to rewrite, okay? So the goal of this is to rewrite each of these as a base with one exponent, okay? So we want to get these down to one number with an exponent. Doesn't look like it's going to be really easy to start. But here's the thing. If we look at the first one, we have to think about what base we want. The idea is to get everybody to the same base if we can, or to a base, you know, a couple of bases that are close and we can do some combining, right? So 2 to the 6th is about as simplified as it's going to get. But 8 is actually a power of 2, isn't it? So I could rewrite 8 as 2 cubed, and that would go to the 5th power. What about 16? 16 is also a power of 2, isn't it? 16 is really 2 to the 4th squared, because that squared is there. So now I can use my exponent rules. So 2 to the 6th is going to stay. Power to a power, like this one, is multiply. 2 to the 3rd to the 5th power is 2 to the 3rd 5 times. 3 5s is 15. And then 2 to the 4th squared, it's 2 to the 4th twice. That gets me 8 2s. Now they're just all multiplied together. I can add them. 6 plus 15 is 21. 8 is 29. So this is 2 to the 29th. So what I did was take this big old mess up here and rewrite it as 2 to the 29th power. They're equivalent. The second one is a little harder, right? Because they don't simplify down quite as well. But they do, actually. You just got to give it a minute. So think about the base you might want. Okay, for sure I can see a base of 3 in here. But 36 isn't going to do that nicely. Well, maybe it is, partially. So let's think about 36 first, because that's the hard part. So 36 is a number with, oh gosh, and I wrote 39. I don't mean that. 36 is a number with factors, right? Is there a way to get a factor that I could get a base of 3 out of? Well, I could rewrite 36 as 9 and 4, right? And that would be 3 squared and 2 squared. So maybe I'll use that instead of 36 because it's equivalent. All right, so 9 I could rewrite as 3 squared. Let's do that. 3 squared to the power of 4. Okay. And then I have 36, which I decided to rewrite as 3 squared times 2 squared, all that to the power of 5. And then that whole thing is divided by 3 to the 18th. And honestly, I have an easier time thinking about that if it's in the bottom. So I'm going to make it a fraction. It's just an easier way to look at it with exponents to me. So let's do the working out here. So 3 to the squared 4 times gets me 3 to the 8th. Okay. Times, now I have to distribute this guy. 3 to the 5th, 3 squared to the 5th is 3 to the 10th. Times 2 squared to the 5th, that's 2 to the 10th. All right. And then 3 to the 18th on the bottom still. Well, oh, do you see what's going to happen? 3 to the 8th and 3 to the 10th makes 3 to the 18th. That 2 to the 10th, I can't combine. The exponents are different, so I'm sort of stuck. And on the bottom, I have 3 to the 18th. Well, what's going to happen here? Those guys are going to cancel. All I'm left with in the end is 2 to the 10th. All right? So take your time and work through this on your own. It's actually worth doing one of these a second time. If you would want to do, you'll see some of them in the homework, but it's okay if you like stop this, rewind, try them yourself, just to make sure you can do the process. All right, so let's start talking about multiplication algorithms. If we look in multiplication, one of the things that we can do is take apart numbers. This number across the bottom is 13. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 3, right? And I want 3 of them. So think about 13 times 3. What this picture is telling me is that I can take this apart, right? I can think of this as 10 plus 3 times 3. So this 10 times 3 gives me 30. And this 3 times 3 gives me 9. If I add those together, I get 39. 10 times 3 and 3 times 3. That's what this 1 up here in the 13 really stands for, isn't it? It's a 10. This is actually what's called the partial products model, or I think they call it left to right multiplication. Basically, it's the idea of distributing, sort of. I think of this 13 as 10 plus 3, and then I distribute the what I'm multiplying by, okay, to it. So 3 times 10 and 3 times 3 gets me 30 plus 9, gets me 39. Oops. This is a really important thing to think about. It actually makes your mental math a lot easier. Okay, so let's think about it. The other thing that we do to help kids is multiply by 10, right? So if I take 23, 1, 10, 20, 1, 2, 3, and I multiply it by 10, basically what I do is I take each piece and move it to the next pattern block up. Each of my ones becomes 10, right? 1 times 10 is 10. 10, 20, 30. Each of my 10s becomes 100. 10 times 10 is 100. 10, 100, 200. So I have 100, 200, 10, 20, 30. So 23 becomes 230 when we multiply by 10. You know that, but you may not have done it in pictures like this. All right, there is a game in here about partial products. So that's one of those things you're going to have to try, okay? We're going to do a separate example for partial products right here because we would do that. Actually, we'll do it next. It's coming. Oh, I did these in out of order. Notice that this, if I do 23 times 10, it's still really similar to distributive, right? I took my 23 apart to 20 and 3. I multiplied 20 times 10, or right? This is, or 2, 10, 10 plus 10 times 3. That's really what we did in the pictures, right? 10 plus 10 times 3. So you can think of that either way. So I get 100, I get 30, and I don't have any ones. All right. Any kind of multiplication by a power of 10, we just know you can complete by appending zeros. Like if I'm multiplying by 10 to the first, I add 1 0 onto the end of my number. If I'm multiplying by 10 to the second, I'm adding 2 zeros onto the end of my number. If I'm multiplying by 10 to the third, which is the same as 1,000, I'm adding 3 zeros onto the end of my number. Kids don't always know that right away. It's not like they're innately born with that. That's something you teach them, okay? It's actually a really important skill. So we can take that idea apart and do it with numbers that are 2 digits. You can do it with numbers with 3 digits. Here's how it goes. I'm going to do 23 times 14. So I'm going to do it out here. So think about first, this is the number 23 across the top. 2 10s, 3 1s. Okay? Across the side, I have 10 and 4, so that's 14. 23 across the top, 14 along the side. So I'm going to think about what I get. So I have 23 and 14. I'm going to do each product separately. So take them apart number by number. This 2 stands for 20. I'm going to multiply it by the 1 that stands for 10. 20 times 10, 20 times 10 is 200. And that is right here in the picture, 20 times 10. And then I'm going to multiply my 20 again times 4. Well, that's right here. 2, 3, 4, 5, 6, 7, 8. 20 times 4, right, is 80. Okay? Then I'm going to multiply, I'm not going to look at this. This 1, well, that's not really a 1, though. It's a 10, right? It stands for 10. By the 3, okay? So 10 times 3 And I see that right here. 1, 2, 3, tens. Gets me 30. So I took care of 20 times 10, 20 times 4, 10 times 3. And now all I have left to do is 3 times 4. That's going to get me 12. And I see that 12 right here, right? So now all I have to do is add 2. Let's see, 8, 9, 10, 11, 12. Carry the 1, 322. So 23 times 14 is 322. And I can use this picture, or I can use the partial products. So let's do another one. Let's try, I don't know, 64 times 23. You try it. So take a pause and see if you can do it. All right, so I'm going to go through my parts. That 6 stands for 60. I'm going to do 60 times 20. 60 times 20 I know is 1,200. All right, and then I'm going to use my 60 again times 3. That's the other part of 23, right? That makes 180. All right, now I'm going to use my 4. 4 times 20 is 80. And 4 times 3 is 12. I want you to look at the list of partial products here. What do you notice? I, as a teacher walking by, can tell you when you did it right just by sort of glancing. I don't even really need to see much more than that. Think about what I'm looking for. What I'm looking for is I want to see each number used twice. This is made of 60 and 4. This is made of 20 and 3. So I see 2 60s, 2 4s, 2 20s, 2 3s. I'm pretty sure all your quotients are, or your products are right. So now I just have to add 2. 8 and 8 is 16, plus 1 is 17. 4, 1. 1472. And I bet if you got out your handy dandy phone calculator and you checked it, 64 times 23, you'd get 1472. This is partial products. This is a way that every kid can do and they love. And this is how I do math in my head. All right. The second way we need to know is lattice. Lattice is is referred to low stress sometimes because it's really about single digit multiplication. Some of you may know and love lattice. This has been around for ages. This is like an ancient method, which sometimes is taught in schools and sometimes is not. Some kids love it and use it and can't get rid of it and want it all the time. And some kids it's too many boxes for. Okay. So when we multiply with lattice, what we do is we set up a rectangle. This one is 2 by 2, 2 rows of 2 boxes, okay? Because I have 2 digits by 2 digits here. One number goes across the top, 10 and 4 for 14. The other goes along the side, 2 and 3, or 20 and 3 for 23. And then what we do is we multiply inside the boxes. 4 times 2 is 8, so 0, 8. 1 times 2 is 2, 0, 2. 1 times 3 is 3, 0, 3. And 4 times 3 is 12. Every lattice box has a diagonal. And when you're done, you add down along them, just like we did with addition. Okay? So 2 and nothing is 2. 8 and 1 and 3 is 12. Carry the 1. 1 and 2 is 3. My answer is still 322. So let's do 45 and 67. You try it. I'm going to draw my boxes. Hopefully not have them be a mess. I would not be the kid that did this. So my box is going to be 2 by 2. And your diagonals go corner to corner. So be careful. Diagonal, diagonal, diagonal. Okay. So I have 45 times 67. So far, so good. All right, let's 4 times 6 is 24. So I'm going to put 2 in the tens place, 4 in the ones place. 5 times 6 is 30. 3, 0. 5 times 7, is 35. 4 times 7 is 28. And now we add down diagonals. 5 becomes 5. 0 plus 3 plus 8 is 11. Carry your 1. 2 and 4 is 6, plus 3 is 7, 8, 9, 10. Put down the 0, carry the 1. We get, so our answer is 3,015. All right, see how that goes? You will get a chance to practice. And on the test for this chapter, you will have to do certain methods. You're going to have to show them all. So it's not just going to be the method you like. You have to prove that you can use them all. Okay, so that's the multiplication processes. Let's move to everybody's favorite part, division. All right, so let's start with just a question. There's a shopkeeper and she's putting juice into cartons that hold 6 bottles each. She has 726 bottles. How many cartons does she need? So you do that first, no calculator. Whatever way you do division, how do you figure that out? All right, for me, I use something that's called partial quotients. Okay, this is another way they teach kids now. It is certainly, to me, a good alternative to long division. Long division is misery, and it's what most of us learned in school. It starts out the same way, though. I'm going to divide 6 into 726, and that's where it stops. Okay, so I'm going to use numbers that are really easy. I'm not going to worry about what exactly fits into where. I'm just going to do what comes to mind and subtract. This is how I get to partial quotients. So I know, for example, that 6 times 100 is 600. And I could take 600 out of 726 pretty easily. So I'm going to do that. So I'm going to put 100 over here on the side. That's where I keep a running list of what I've subtracted. And I'm going to subtract 600. That gets me 126 left. All right. Well, what else would be easy? 60, right? 60 would be easy. I know that 6 times 10 is 60. So I'm going to take away, oops, I'm going to put 10 here, and I'm going to subtract 60 from my 126. That gets me 66. Huh. Well, I'm going to be lazy. I know that I could subtract 60 again, right? That's another 10. So I'm going to subtract 60 again. And I'm going to get 6 left. Well, that's 6. 6 times 1 is 6. I'm done. What I have to do to get my answer is add up how many 6s I used. So that's 100 plus 10 plus 10 plus 1. That's 121. So the answer to my problem, 726 divided by 6, is 121. That's partial quotients. So there's lots of ways to, here's the thing. If you use different partial quotients, great. You use 60 a million times, fine. Used 120 maybe. It could be at this stage right here, you thought like, well, I know 60 times 20 is 120. Okay, fine. Use 10 and 20 instead of 10. Doesn't matter. What matters is that in the end, you get where you're going. The more kids use a method like this that uses sort of their sense of numbers, the faster they'll get. So here's what it looks like. I did 100, 10, 10, and 1. I could have done 100, 20, and then 1. Either way, I get to the same place, okay? There is, you can do this all in base 10 blocks. It's a bunch of slides here. I'm going to flip through them. Take some time and think about this. You might pull up the PDF version of these to look through them. We're not going to spend a lot of time talking through it. So I have my 726. I can represent the hundreds and I can separate that into groups by 6. I can break up what's left and continue to group by 6s. So I have a group of 100s, one group of 10s, one group of 10s, and one group of 6s. Still 126. I know, or it's 121, sorry, too many 6s. So that's one way to do this. You'll get some practice in the homework. Oh, wait, no, I want to do a different one. I have an example. I'm going to make us a new page if I can figure out how to do that. All right, so let's try 296 divided by 8. 296 divided by 8. Okay, so you try it, partial quotients. Okay, so for me, I'm going to set it up. All I do is think about what's easy. For me, let's see. I know 8 times 10 is 80, so let's do that. I'm going to take away 80. That seems painless. So I get 216. Okay. Well, I don't have to do this in any order. For me, I know 8 times 2 is 16, and I'd really like to get rid of that 16 because I don't really want to subtract so much. So I'm going to subtract 16 next and just get 200. Okay. Now what do I do? I guess I could take away 80 again, right? So another 10 eighths. 200 minus 80 is 120. And I'm sure I could do that again, right? Let's do it again. Minus another 80. That gets me 40. Oh, well, that was 10 more eighths. I know 8 times 5 is 40. So I'm done. Huh. So what did I use here? 10, 20, 30, 35, 37. So 296 divided by 8 is 37. Okay? This is the process you're going to try. All right, the next method is called short division. Short division is sort of like long division without all the work. I'm actually going to do it below here so you can see it work. So I'm doing 5 into 2,880. Okay, start here. So you go, 5 goes into 28. Okay, you look at the first, you look at sort of the same long division process. 5 doesn't go into 2, but 5 goes into 28. 5 goes into 28 5 times, right? 5 times 5 is 25. So I'm going to put a 5 here. And then what's left over? 28 minus 25 is 3. So I'm going to write that 3 right there. Now I'm going to look at 38. 5 goes into 38. 7 times, right? 5 times 7 is 35. So I'm going to write a 7. 5 times 7 is 35. 38 minus 35 is 3. Okay, so there's my 3. 5 goes into 30. How many times? Let's see, 6. So it's 576. Goes in perfectly, no remainder. But if there was a remainder, I could write it right there. Okay, did you follow? Do you want to try it again? So let's do, we could do 726 with short division. Let's do that one. 6 into 700, that's too easy. Let's do, which one did I just do? 296 and 8. Let's do that. All right. 8 into 296. Okay, so 8 doesn't go into 2, but 8 does go into 29. 8 goes into 29 3 times. 3 times 8 is 24. There's 5 left over, right? So I'm going to put the 5 right in front of my 6. 8 goes into 56. 7 times. 37. Same answer as before, right? Interesting. Okay. So those are the multiplication and division algorithms. The other thing that we have to do is multiply and divide in other bases. So multiplication, division, other bases. Division by a two-digit divisor. Why? I think I took those out of my slides. Estimate, multiply, subtract, check. Okay, so this is really just like an estimation process. Think about how you would follow this. We think about estimating first. I know, like, for example, if I think about 32 is going into 2,618, it's got to be less than 100, right? Because 32 times 100 is 3,200. So my answer is going to be less than 100. I think it's going to be more than 50, though, because half of this would be 1,600. and that would be half of 100. So it's got to be more than 50. So then you use sort of that to think about your division first, and then you do some multiplication and subtraction. You sort of guess and check. But you could still use partial quotients here, and I would. I'd start subtracting 320s. All right, so let's start with multiplication tables. I just am missing a whole page here, and that is my problem in my notes in front of me. I just lost one. So let's create a multiplication table for base 5. Let's set up what goes in here. So 0, 1, oh, sorry, they should go in the boxes. 0, 1, 2, 3, 4, right? 1, 2, 3. I need my table. Sorry, my brain, I'm missing pages. Where's my multiplication table? Oh, there it is. How did I have it set up? Ah, that's why I needed zeros in both places. So let me clean this page up. I knew my table was going sideways. Okie dokie. Okay, here we go. There it is. I had a multiplication sign right there. That was my problem. I had too many boxes. 2, 3, 4, because we only have 0 through 4 in base 5, right? Okay, let me change colors so we can do this out. So 0 times 0, 0, right? Anything times 0, 0. So I can just fill in my zeros. Now I want to think a little bit. This is base 5, right? So let's think first about counting in base 5. I find that really helpful. So I'm going to make a little chart here, a base 5 versus base 10 chart. So in base 10, I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, right? In base 5, I go 1, 2, 3, 4, 10, right? 11, 12, 13, 14, 20, 21, 22, 23, 24, 30, 31, right? That's going to help me. Okay, so 1 times 1, oops, get your pen back, is 1. 1 times 2 is 2. 1 times 3 is 3. 1 times 4 is 4. So far, this is pretty easy. 2 times 1 is 2. 2 times 2 is 4. 2 times 3 is 6. Oh, nuts, I don't have a 6. But I can look, right? 2 times 3 in base 10 is 6. What is that worth in base 5? It's worth 11. I'm going to put an 11 there. Then let's do 2 times 4. 2 times 4 is 8 in base 10, but what's that worth here? It's worth 13. And the other way you can think about this is you can actually count. Let's see. 2, 4, 6, 8, right? I can do jumps of 2. The next 2 would be here, okay? Now let's do 3s. 3 times 1 is 3. 3 times 2 is the same as 6 again. I already know that 6 is worth 11. 3 times 3 is 9. Let's see. So I could count from 11 over 1, 2, 3. 1, 2, 3. That's 14. That's the same as 3 times 3 in base 10 is 9. And then we need to count over 3 more. 1, 2, 3. That's going to be 22. So 3 times 4 is 22. Let's see, 4. We already know 8 is 13. 4 times 3 we know is 22. What about 4 times 4? Well, let's count 4 more from 22. 1, 2, 3, 4. It's going to be 31. Okay, see, this is a multiplication table in base 5. This is very strange, isn't it? But we're going to use this table to help us multiply. Okay, so let's try one. I'm going to make these base 5. All right, I want to multiply 43 times 23 in base 5. Okay, so I'm actually going to do this. Let's see. Like this. Okay. Well, we can go pieces, right? I know, let's see, I have 40 times 20. I'm going to use partial products. Well, 4 times 2 was 8. 4 times 2 was worth 13. Well, that's going to be 13 with 2 zeros, right? So 1, 3, 0, 0. Then I'm going to do 40 times 3. 4 times 3, what was 4 times 3? 4 times 3 was 22. 4 times 3 is 22 with 1 0, that's 2, 2, 0. All right, and then I'm going to do 3 times 20. Well, 3 times 2 is 6, right? What's 3 times 2? That makes 11. So that makes 11 with a 0, right? And then I have to do 3 times 3, which was 9. What was 9 worth? 9 was worth, 3 times 3 was 14. Okay? Then I have to remember that I'm adding in base 5 as well, okay? So 0 plus 4, that just makes 4. 2 plus 1 is 4. But here's the thing. 3 plus 2 is 5, plus 1 is 6. But remember, we're in base 5. So 1. In base 5 and base 10, 6 is worth 11. Okay, so I'm going to put down a 1 and carry a 1, just like I would add. So my answer is 2,144 in base 5. If you need to see it again, go through it, okay? Try it. You can always re-watch these or rewind, okay? Now let's divide. So I need to do this in base 10, or sorry, not base 10, base 5. I'm dividing in base 5, so I have to think about this as base 5, all right? And I have a, there it is. Let's start with something smaller though. Let's do 32 divided by 3 in base 5. Okay, let's think about it this way first. So think about if I counted in base 5, and I did back here, all the way to 32 and I divided it by 3. So let's count in base 5. I go 0, 1, 2, 3, 4, 10, 11, 12, 13, 14, 20, 21, 22, 23, 24, 30, 31, 32. So there's our number. I need to divide it into groups of 3, right? That's what division is. So let's think about it that way. So here's one group of 3. Here's another. Here's another. Here's another. Here's another. And then there's 2 left over. So how many 3s do I have? 1, 2, 3, 4, 5. I have 5 3s, but I don't have 5 in base 10. That's the same as, or sorry, in base 5. That's the same as being worth 10. So the answer here is going to be 10, remainder 2. Okay? So you can think about division as grouping when they're small like this. But when they're bigger, we still use our same algorithms. Okay? So I'm going to make myself a new page to do this one. And I keep losing that skill. So 3241 by 43. Okay. So let's think about it in tens, right? But we have to calculate in base 5. We still think about it. I still can take away groups. Oh gosh, do I really want to do this one with you? Probably not. I feel like on the online. I do this one in person with my in-class kids, but I have to say I think the translation of this via this mode without you being able to ask questions is kind of complicated. So maybe we'll stick with the simpler ones for the moment, and kind of as you practice, you'll see they don't get in the homeworks much harder than the 2-digit ones. So I don't know that we need to go much further with that. Let's do one other short one. So instead of doing this, let's do something like, 421 in base 5 divided by 4. Okay, so how could we do this? Well, we could use our short division skills, or however we wanted to do. I know 4 goes into 4 once, right? 4 doesn't go into 2, so that's a 0. Does 4 go into 21? Well, let's go back to our base 5 table. If we think about counting 0, 1, 2, 3, 4, 10, 11, 12, 13, 14, 20, 21. Let's think about how many groups of 4 are there. So here's 1, there's 2. So it goes in twice, and we have a remainder of 3. Okay? What you have to do is continually be thinking about how to count in the base you're in when you divide, which can be complicated. But let's stick with the simpler examples here. The multiplication, you're going to be fine, and we'll go from there. So the end of this section is more, just like we did in the addition and subtraction section, is more mental math. Okay, so we can think about front-end multiplying, which is really just another way for thinking about partial products. So I think about 60 times 5 and 4 times 5. So that's 320. That gets me 320. Okay. The next one, I turned the page, not the slide, is compatible numbers. Just like you would add, you would group things to make them nicer. For me, I would do it like this. I would reorganize a little bit. And if I do that, I get 10 times 100 times 9. That's way better than what I could have been doing here, because that's 1,000 times 9, which is 9,000. Oops, I missed a 0. If I did that out of order here, it'd just be way more complicated. So you can reorganize numbers because multiplication is associative and commutative, whatever order you want. The other thing we can do is think about money for multiplication. So I can think about 64 times 5. We just did that. We know it's 320, right? No, it's not. Yeah, it is. Okay. But I can think about in quarters, right? So if I did 64 times 25, what I really have to think about is there's 4 quarters in $1, right? So I could make this groups of 4. So for every 4 in 64, I'm making a 100. 4 times 25 is 100, right? So 64 divided by 4 is 16. 16 times 4 groups of 25 is 100. It makes 1,600. It's crazy, right? You'll have to think through that one a little bit, see if you can make sense of it. I can do the same thing with 50s. I know that 2 50s is 100. So instead of thinking 50 here, I can think 100. But if I'm going to double this, I have to use half as many 64s. So I'd use 32 of them. It'd be 3,200. Okay? This is sort of like using 4 times as many 25s and a quarter as many 64s. That's what we just did. Okay? When we divide in mental math, we can think about breaking up the dividend. So I can think about this because 7 goes into 42 nicely and it goes into 56 nicely. I could think about this as 7 into 4,200 and 56, right? I don't want to just do it into 42 and then 56. That's not really what that 42 stands for, right? So 7 into 4,200 is 600. 7 into 56 is 8. So my answer is 608. Okay? One more, compatible numbers. Sometimes you can break up the dividend in a different way. Like here, we just used the place value. We made 4,256. Sometimes that's not helpful. Here, 105, I could make 10 and 5. Like, what good did that do me? But 105 is actually made up of 90 plus 15, isn't it? Well, I can divide 3 into those guys really easily. 3 into 90 is 30. 3 into 15 is 5. That makes 35. Okay? So this is a strange section over notes. So do your best. Ask questions as you have them. You're back from break. You're feeling good. Practice. You do have to be able to use all these algorithms, the addition ones, the subtraction ones, the multiplication ones, the division ones, when you're called upon to use them. You will have to do that. So please know how to use them. Practice. Ask questions as you have them, and I'll talk to you in the next section.